We're really pleased now to introduce Professor Melanie Cooper to round out the day before we do some more mixing over the reception. Melanie is at Michigan State University. She's a professor of chemistry and the Lappan-Phillips Professor of Science Education. Her own training has been in the UK at the University of Manchester, both for her bachelor's and PhD. She's then completed postdoctoral work in organic chemistry at Clemson University. And she's a internationally recognized and renowned scholar in education and focused her career on understanding, teaching, and learning in large classes in general and organic chemistry, and a leader in evidence-based curriculum reform. Her dedication to the improvement of teaching chemistry in higher ed, again, is well recognized. She's a member of the National Research Council Advisory Board on Science Education and has been recognized with really important awards, the ACS Award for Achievement in Research on Teaching and Learning in Chemistry, the Norris Award for Outstanding Achievement in the Teaching of Chemistry, and also the Outstanding Undergraduate Science Teacher Award from the Society for College Science. And she's really turned teaching into a science, and it's going to be exciting to hear about your work here. And I think the title of the presentation is, What Can Theory and Evidence Tell Us About Teaching and Learning Chemistry?
Thank you. Thank you very much. It's really a pleasure to be here, and I thank you for waiting around to hear what I have to say. Maybe it's the lure of the drink afterwards, but I hope that I will challenge you. I think I'm probably going to offend some of you. I think. I hope that you will take something away from this talk, because what I'm going to say probably is not what you think I'm going to say. So I was going to give you my straight research talk. We have got a pretty long history of doing chemistry education research in my group. But then, you know, things happened. And it dawned on me that what we do matters, and people care a lot about what we do, more than perhaps we think. So, you know, I was surprised when I got up one day and saw this on the front page of the New York Times. We all know about this. We all have an opinion, and so did 6,000 other people in the comments. People just roared out of the woodwork, right? Maitland Jones, a respected professor, absolutely true, was let go by NYU because students complained about him. They complained that They complained that the course was too hard, that they weren't being recognized for all the work they were putting in, and so on and so forth. And then the university dismissed him. And depending upon who you are, you have a point of view about this, and lots of people did, right? It's and depending who you talk to, it's like a Rorschach test or Rashomon, you know. Everybody has a different story here. And, you know, Maitland Jones says that students colleges coddle students. And maybe they do. But in CNE News, the chemistry professors decry the firing of their colleague, startled and disturbed. Chemistry professors say NYU is to blame for firing him. And there was some interesting comments in here. They say it's a problematic system of teaching organic chemistry in which chemistry majors and non-majors take separate classes. I don't know how problematic that is. But the real problem was the pre-med students. They're required to take the course and they focused on grades. And many who signed the petition were pre-med students. And we know all about pre-meds, don't we? International. So here's The Guardian from my own home country. Front page, you know, organic chemistry, here we are. So in here, parents and teachers say they're lowering academic standards. We are not being rigorous enough. And then, though, things started to get a little more interesting. So here we have something from New York Magazine. Maybe those whiny grade-grubbing NYU students have a point. You know, maybe we need to think about what we're doing a little more carefully. Why is it so hard to get into med school? Why do med schools expect us to screen their applicants? And here from the Washington Post via Bloomberg is an even more thoughtful, this one is a thoughtful piece. Maybe the traditional weed-out model of medical education, where there's an understanding that patients get better care from doctors who've been in this traditionally competitive organic chemistry class. Maybe the survival of the fittest, maybe those aren't the best doctors. You ever think about that? Maybe the better doctors are the people who've been nurtured and supported in their work. Maybe. All right. So, and then Holden Thorpe, our own Holden Thorpe, entered into the fray, and he's really unhappy. Stop passing the buck on intro science. And I think I want to echo that. We have to stop passing the buck on intro science. It's not okay. The way we teach intro science, it's not okay. Right? We are failing people, and pre-meds are people. They're our future doctors. I don't want to go to the doctor anymore and have the doctor say, oh, I hated organic chemistry. I've never used it again in my whole life. We need to think carefully about that, or they're going to take it away from us. You know, they're going to take the teaching of these intro courses away. And when that goes away, so go our graduate students, and so go a lot of the FTEs for the department. So it's something to think about carefully. We need to pay attention and not just cast blame on someone else. All right. At the same time, last week, we get a new Boyer report. Now, most of you in the room are too young to remember the old Boyer report, but it had some wonderful recommendations. I think it was in 1998. It said we should take teaching seriously. It said we should, we should look at the culture of the science departments. We should look at the reward structure. Have we done that? No, we have not. All right, so they've come out with a new report, and in this one, they're not only saying all the other things, but they're talking about this equity, excellence imperative, right? And I think the major thing that I want to have you focus on is, can we commit to equity as a necessary and defining precondition of excellence? Okay, so this is something to think about. The great students in our classes, the elite students in elite universities are bulletproof. It doesn't actually matter what we do. They're going to learn. But there's a vast number of students out there who could be great if we gave them the opportunity. If we didn't cut them off at the knees in our intro courses and expect them to go through all kinds of rigmarole. So I want you to think about this. It's really worth considering in your own heart, because you're the future. All right. Do you see yourself as a weeder or a gardener. In your courses, are you weeding out students? Are you curving your grades? Because you know where grade curving came from? It came from the eugenics movement. Seriously, that's something to think about. Or are equity and rigor incompatible? The Boyer report doesn't think they are, and I don't think they are. And besides, what does rigor mean? You know, rigor is in the eye of the beholder, isn't it? So there are a lot of students who we're not serving very well right now. And I want to convince you that we can serve and support all students. Not everybody's going to succeed. I don't mean that we're going to end up with, you know, 3 billion chemistry majors, but we have to prepare students for STEM careers, and we want them to succeed. We don't want them to, we shouldn't be weeding and sorting students. All right, but it's going to require significant and systemic change. And here's my point. We can't do this without thinking about theories of learning, right? We can't just say, oh, I've got a good idea. You wouldn't go in the lab and say, oh, I've got a good idea about, I don't know, whatever it is that someone else does over there. I don't really know anything about it, but I'm going to do it now and I'm going to be successful. You would look up all the background, you would look up the theories, you would look up what people had done before, and you would build on it. But we don't tend to do that in education, because education, we've all been educated and we all know how to do it. And we are all good at it, right? We're all better than average teachers, and it's extremely personal to us. There's nobody who goes into the classroom saying, I'm going to do a bad job today. We all think we're doing a great job, but we're not, because we're not supporting enough students. Okay, so here's now my standard research talk after that little harangue. So I'm not going to go into a full, you know, hour of theory now, but one of the things that we know is that experts and beginners have different knowledge structures. And so experts have this kind of underlying framework of knowledge that they can use and build on. It is useful knowledge, in fact. And when we teach students, we have to teach them bits and pieces. We can't teach them a beautiful framework of knowledge off the bat. We got to teach them bits and pieces. But that knowledge is inert until we help them use it and connect it. So that's our goal. There we go. That's our goal, right? We want them to connect this knowledge. And when we do that and we get them to a more expert-like framework, then when new knowledge comes along, it can be used to support that new knowledge. That new knowledge can be connected into the framework, and the student, the nascent expert, can use it. And I think that's our goal. But it's all too easy to concentrate on the fragments, right? We teach the fragments and we often test the fragments. And so I'm going to give you an example from the ACS. You're not going to like this, but the ACS Exams Institute has developed what we call anchoring content maps and for use in exam development. And what they do, and I just want to say that these are overarching concepts, which is a good idea. There are a lot of projects that have developed these ideas of overarching concepts. And so the ACS, bless you, has, this is for general chemistry, have developed, I think they've got 13 or 14 now, which is way too many. But anyway, so they have an anchoring concept here of bonding, right? Bonding. And whatever model we want to think about in bonding, this is the model that we're using in general chemistry. But then they split it up into smaller bits, okay? And in this, we get one of the fragments is breaking a bond requires energy. Now, if you know anything at all, you know your students don't know this, right? They think that breaking a bond releases energy and it flows out and like in ATP and drives reactions, which is, you know, not true. And then we split it up again and that, whoa, what happened there? Let me back up a minute. Sorry. You're getting my whole talk all at once. This is useful. Back up. Come on. Ugh. Great. You spoil all my surprises now. Back up. Okay. Bond dissociation energy. There we go. And finally, they break up this into, what do they call it? Content details, right? These are the fragments, the content details. And the ACS says, assess at this level, right? They explicitly say, this is where you should assess. And the reason is that you can write psychometrically valid tests on little bits and pieces of knowledge. But the problem is that when you do this, this Mickey Mouse calculation here, there's absolutely no connection to the core idea of bonding, right? So students can do this calculation without knowing any of this other stuff. So what we want to do is we want to help students connect and use their ideas. And there are lots of ways to do this. The way we do it is we use what the National Academies call the scientific and engineering practices, actually. These things that scientists do. And you can see, scientists do develop and use models. Scientists construct explanations, engage in argument from evidence. They use mathematical and computational thinking. And once you have defined these things, then you can assess them. And so, yes. So we want to assess by helping students connect knowledge. And so here's a task that is straight out of general chemistry. If you've ever taught general chemistry, you've done this, right? Use the table of bond energies to calculate delta H. There is no chemistry in that question. There's no core idea. All you're doing is shoving numbers into an equation. But if you have students re-represent the finding from that, they could graph it, they could explain it, they could do something. Then they're making a connection. And here, if you have them graph it, then that falls under the purview of mathematical thinking with the core idea of energy. Energy is a big idea. We might have students draw the structures, use those as a model to identify what bonds are broken and explain why breaking bonds requires an input of energy. And when we do that, we're having students construct models and explanations. We might add on then at the end, construct an explanation for why the energy changes when a reaction occurs. Okay, so what we're doing here, this is a much more involved kind of thing, obviously, but we're helping students connect their knowledge. And you can do this across the board. We have plenty of examples. But you're saying, oh, but my students do that. In my class, my students do, we may not call it scientific practices, but we do it, right? So in fact, no, you don't. So this is a paper that Ryan Stowe, who was a postdoc with me and now is an assistant professor at the University of Wisconsin, he roamed the internet for elite universities' organic exams, which they proudly post on the internet. And I won't tell you which elite ones, but they're pretty elite. And what we found was that the exams actually didn't have scientific practices in them. They were hard. not saying they were easy, but they didn't ask students to use their knowledge. What did they ask students to do? Well, what we did was we asked students, what do you think you're being assessed on? And we asked them to write it out. You know, what do you think? What kinds of thinking are you assessed on? And what students said was memorization. Now, I guarantee you, this was not the intent of the instructors. I guarantee you, I don't know any organic professor who says the main goal of this course is for students to memorize stuff. But that's what the students thought, and that's what they were doing. And that's a problem, right? So, okay. So what we did was, over 10 years ago, we began transforming our curriculum. We got funding from NSF, and I got myself a collaborator, actually, who is a biologist, Mike Lankowski. And we first developed Chemistry, Life, the Universe, and Everything, with apologies to Douglas Adams. And secondly, Organic Chemistry, Life, the Universe, and Everything. So we now have 4 semesters of what we call this transformed curriculum. And there are lots of components to this curriculum, but the major aspects were developed by thinking about backward design, which is you start out at the end. What do you want your students to know and do? And then you go and make sure that you design a curriculum that can do that. So we design the curriculum and the assessments. We assess student learning. And we use those results to redesign the curriculum. So one-shot deal doesn't really work. And most published curricula don't do this. So you start out with a hypothetical kind of sequence of events, and you end up with an empirically tested curriculum that you feel comfortable that students are potentially learning something. All right. So these curricula are developed around carefully sequenced progressions of core ideas. So this is back to that connecting your knowledge to these larger pieces of knowledge so that you have more robust knowledge structures. So here are the core ideas for clue. And, you know, most phenomena in chemistry require connections to more than one core idea. But they're not topics. There's not a chapter in there on, you know, structure and property relationships or energy. You know, every phenomenon that's discussed in the curriculum is connected to at least one of these core ideas, and students work with these ideas in the context of the scientific practices. All right, and I'm not going to go through all the evidence. We have a lot of evidence because at certain points, as we transform the curriculum, we've had the capability of comparing matched cohorts of students in traditional courses and in transformed courses. So we know things like students in the transformed courses know about non-covalent interactions, for example, which are not bonds in the traditional sense. But many students think that. Students can predict properties from structure, which is an important capability. Students can give causal mechanistic reasoning. They can think about phenomena in chemical phenomena and give explanations that give the mechanism and the causal reasons for why things happen or why things don't happen. and more traditional things like drawing mechanisms, right? So we've done a lot of studies, and I'm not going to go through them all because it would take a long time. But I want to go back to this idea. We do have a lot of evidence that students from transformed curricula are better at certain tasks that we value. But is the curriculum equitable and is it rigorous? You know, are we just dumbing it down? So we were worried that people would say that. Is it equitable? So we'll start here. So what happened, year 0 was the old curriculum. And over time, as more sections transform to the new curriculum, we see that the GPA goes up, the average GPA, and the percent of D's, F's, and W's goes down. And this actually is quite interesting because we teach so many students at MSU. This translates to, in a year, more than 700 more students making a C or better in the course, which means they can carry on. So if you think about that, that's a lot of students. That's a lot of students who were cut off from their dreams in the old version. And I can see that some of you are sitting there going, yeah, but they don't deserve it. They weren't good enough. The old. Well, we don't all teach at Columbia. So, yeah. So what we did was we gave the national ACS exam, and the students do fine. They are not below the national average. They're doing just fine. And even though I don't like the ACS exam. And what we also found was that students who, when they go on to the next courses, do just as well as students who take the special sections, the honors students, the chemistry majors, Lyman Briggs, which is a residential college at MSU with small classes. So our big, marching cohort of 5,000 Gen Chem students are doing pretty well. And we're starting to see, it's hard to do cause and effect when you're talking about a freshman course and graduation rates, but we are seeing our graduation, time to graduation go down and retention in the college starting to go up. And here's another study that we did not do. This was led by Vanessa Ralph and a couple of other faculty. And one thing that you may or may not know is that in general, these big general chemistry courses are very inequitable. Their grades are highly correlated with math pretest, or math ACT or SAT. So you might think, well, why do we bother teaching them? We'll just take their math SAT test and just move them on straight through. So what this means is that students who come from underprepared backgrounds, so the lowest quartile of math prep, are starting way back in this race. They've got a much further to go to be able to move forward in this race that we've set for them. And what Ralph and co-workers found was that indeed, when you look at students' scores on questions in Gen Chem that come from the math part of it, and this is our data that they analyzed, it looks just like this, right? They're inequitable. Students who are underprepared in math don't do well at all. But if you look at the kinds of questions that I showed you later, the mechanistic reasoning, there's still some gaps, but it's not as large. There will be more, and there are more students pass the course when we ask these kinds of questions that don't rely so heavily on disembedded math questions, stoichiometry that's got no relation to chemistry, you know, delta H calculations that have got no relation to chemistry. So I find this very encouraging that we have some indication here that we can be equitable and rigorous. Okay. And the last thing that I want to show you is a set of studies that we have been doing over the last few years about electron pushing. This is a very traditional task. And what we did was we asked students to draw the product of, acid catalyzed hydration of an alkene. This is a simple thing. And most students, not all, but most students in the course can do it. It doesn't matter whether they're in transformed or traditional. They can do it. There's no difference. And you might say, well, so what? But how they get there turns out to be different because of all the ways that we teach them. How they get there is that the students in the transformed course tend to draw electron pushing mechanisms, even for this simple reaction, whereas the students in the traditional course tend to appear to be memorizing it, right? Which, it makes sense, right? It's pretty simple. You can memorize it. So, back to that study on what students think they're assessed on. When we ask the same questions of the transformed students, they think that they're being assessed on use of knowledge. They say things like, oh, I'm predicting and explaining how a reaction will occur, rather than the students in the traditional course. So the students see that there's a difference here. And where we see a difference is, remember, we don't think memorization is the reason we're here. So if we ask students a question that they don't know the answer to, they haven't seen this before, to our knowledge, what we see is, this is sad, by the way, what we see is that students in the traditional course don't do very well at it, right? And I will tell you that this is a replication study of a study we did 10 years ago or longer, and it's exactly the same. So most students can't do that problem. I'm sure all your students could do it, but ours 10 years apart can't do it. But the OCLU students, the transformed students, are somewhat better at it, right? We still got a way to go, but this, we believe, is down to the fact that we're helping students learn to predict and explain outcomes. We're asking them to do these kind of things routinely. So there are a lot more students who are able to think their way through. And this kind of problem in education is kind of the holy grail, right? It's a transfer problem. Can you take what you know and apply it to a new situation? A lot of students still can't do it, but in the course where students believe that they're memorizing stuff, almost none of them can do it. Yeah, so little expert over there. Now at MSU, what happens to students is that they have to sign up for courses a year in advance, and so they don't know where they're going to go. So we still have transformed and traditional organic classes. We've arranged to teach the same material in the first semester, so that they're not at a disadvantage. And but what we see is that there's some weird stuff goes on when students transfer from one type of course to another. So here's the data for that you've already seen for the easy reaction, right? So if students transfer into the OCLU, they get better, but when they transfer out, they get worse. They stop using the kinds of skills that they've learned, and it doesn't take them very long to do this. And we see the same pattern with the unfamiliar prompt, right? So here's the old clue students, here's the traditional students, here's the coming in, there's the going out. Now this is awful, right? It's bad, because what it says is that it doesn't stick. The culture of the course and the kinds of things you ask students to do are all important, and they take their cue from us. And there appears to be this dosage effect. So for example, when we ask students what are the important ideas in organic chemistry and what are they for, what we see is if after one semester, that there's a difference. Again, there's always a difference. It's not very big, but this the orange bit is the fragments, the topics. Students say the important ideas are, nucleophiles or carbonyl groups or whatever the chapter topic is. Whereas the blue bit is sense-making ideas, thinking about how the structure impacts the properties. And what we see is if we take 3 semesters, so if we can back map and see students who went through the transformed general chemistry course, we see that there's a bigger group of students who are thinking about sense-making and fewer topics, fewer fragments. So again, and we're seeing this in other ideas too. So there's a dosage effect. And the point here is, I think that, yes, this one-shot, one-course interventions, they don't work. We need some kind of, and you'll notice I haven't said anything about active learning or how you teach it. That's a given. It doesn't have as much impact as the way we structure the curriculum, I don't think. And I do have some final thoughts here. These are for you. So business as usual is not acceptable, right? We can't continue to fail so many students. Who's responsible though? Who is it responsible for implementing these evidence and theory-based findings? Who should decide what non-chemistry majors should know and do? Is it chemists? Because if we don't shape up, they're going to take it away from us. How will our decisions impact students, especially those who've been ill-served in the past? We want equitable outcomes. And what changes in the culture of our departments and our institutions are needed to implement sustainable change? If we agree that sustainable change is needed. And then we go back to the 1998 Boyer report, which we haven't implemented yet. So there's a cast of thousands here. This is our multidisciplinary group for an NSF project where we're looking at implementing this across the curriculum. And this is my research group, and thanks to NSF and other funding agencies and Mike Klimkowski. And thank you for your attention.